Great. Okay, well, thank you for coming to my seminar today on this topic of electricity markets with storage, and particularly both generation and demand, both stochastic, which is a novel feature of our model compared to the other ones. And this is work I've done with Akshay Shankar, who did a PhD here at Crawford School and is now a postdoc at University of Sydney, and Chandra Krishnamurti, who's at Swedish University Agricultural Science in Umeå, northern Sweden. Okay, so we barely need to motivate this paper. We barely really need to motivate it because it's so, as Paul said, it's very topical, but I will try to motivate it all the same. So the key issue that it's trying to address is there's an increasing share of intermittent renewables, solar and wind power, and that's leading to concern about both the viability of existing electricity markets and their stability, or what will happen to prices in future electricity markets. So there's more and more intermittent generation. And one of the possible problems is a lot of price volatility, okay, or high prices. So last year, the Australian electricity market operator, when the price had been, average price of electricity was above, I'm not sure exactly the number, somewhere around $250 a megawatt hour over a period of a week. Some rule came into play to cap that price. And when the price is capped, as we might expect from the basic sort of introductory economics analysis of rent control and things, supply was withdrawn from the market, and then they suspended the market and started directing generators to actually supply electricity to the market. So this was a sort of unprecedented event in the past, but it was triggered by high price of electricity over a sustained period. The other issue is, will there be sufficient investment? So what will happen to prices, and will there be sufficient investment in both generation and storage using the kinds of electricity markets we have today in the future, when the mix of generation is very different from the historical mix of fossil fuels and some renewable generation we've had up till now. So the government is thinking, Australia is thinking about this, and they had a long process on the post-2025 market design. And the decision so far has been there'll be some sort of capacity market where under the current national electricity market, it is a market which is just primarily where payments are received for supplying electricity to the market. That's called an energy-only market. There are also other services, but they're minor. And be a market where people are rewarded, or generators are rewarded for providing capacity that may be used into the market, as well as for the actual electricity supplied. So they're thinking, in order to no generation capacity. Well, it's looking for a combination, sort of packages of firmed power where there's both generation and storage. But in general, capacity markets are for providing reserve generation capacity, right? In this case, with storage attached as well. So the thinking is that if they don't have this market that rewards generators for providing potential capacity, there will be insufficient generation capacity. So they're looking at further developing this. So we question, well, do you really need that? Well, maybe in our theoretical model you don't. Maybe, who knows, in all the nuances of the real world. But fundamentally, our research is going to show that under sort of simplified market conditions, it's not a fundamental issue which needs to be addressed, but maybe due to other more nuances of things, we might need a capacity market, but it's an issue we're looking at. Okay, so question is, will storage solve these problems of high prices or volatile prices that seem to be caused by introduction of more and more intermittent electricity generation? And then sort of as part of that, addressing that question, what determines storage and generation capacity investment? Okay, so that's sort of the research questions we're trying to address in our paper. So I'm going to talk about a paper which is almost complete. If anyone wants a copy, you can email me and I'll send you a copy of the paper. It's not yet official working paper. And we've been working on this quite a while in between other things. And the paper has a stochastic dynamic optimization model where there's both providers of generation capacity and providers of storage capacity, and we make decisions on how much to invest in both of those. And then there are also hour-to-hour decisions on how much electricity to store for the next period and how much energy to consume or supply to the market immediately. And there's a separation between the generators and the storers. They're different entrepreneurs in the market. So it's a stochastic dynamic optimization. What I'm going to present to you is mostly, I'm going to show you a graphical analysis to get the intuitive points across, and I'm going to show you the simulations we've run with the full model and what that suggests as sort of the outcomes. But I'll talk a bit here about the model. So we're modeling an end state system. So this, the energy transition is complete, okay? And we only have intermittent generation, okay, to keep things simple. But there's also storage, okay? So just storage, intermittent generation, the only forms of generation capacity and well, electricity supply. And we have hour-by-hour consumption and storage decisions, given particular generation and storage capacities, and this is based on the commodity storage model of Deaton and LaRocque. And so we're making decisions given the particular levels of investment. And then basically what we're doing in the simulations is we are simulating lots of different paths based on different given generation and storage capacities, and then optimizing over those to pick the optimal generation and storage capacity. So we basically have a model that does all this simulation of different alternative paths, picks the best investment decision, makes that investment, and then we run the model forward. And the hourly demand and supply shocks, the stochastic shocks to demand, because demand varies. We know a deterministic components of demand, which our model sort of generalizes from, but there are also stochastic ones based on what the weather is and so forth, which change the demand for electricity. And the supply shocks are, of course, due to the weather's effect on wind and solar generation. Now, that is richer probably than any previous model in this area, so we have to make some simplifications just to make things somewhat tractable. And we assume there's no curtailment, so there's always some price where people will demand more electricity. Basically, we have a logarithmic demand curve in the model, and we don't worry about transmission networks or market power. It's competitive markets. Okay, we assume there's lots of small, especially on the storage side, lots of small suppliers of storage. So those are some simplifying assumptions. And in the paper, we show that there's an equilibrium of this market exists, and it's a first best equilibrium. So it's the one the social planner would choose. It's maximizing utility, despite there only being payments for electricity supplied and not for capacity of either generation or storage capacity. Yeah.
Assuming no information-based symmetries, that is everyone equally well informed about whether that's.
Yeah, I could add that to the I mean, you don't know what the shocks will be, but you know the distribution of the shocks. Yes.
Everyone's got that same information.
Yeah, everyone's got that same information. That's another simplifying assumption. I don't think anyone even thinks about what papers I looked at. So
I mean, it could be possible that some of the, I don't know, small providers of storage or whatever else, say, masses of electric vehicles would not have the same information.
Yeah, exactly. That could be true. Yeah. I mean, future versions of the model, once we finish this one, we particularly want to look at sort of the retailer generator divide. And so consumers are not facing the wholesale market directly, which is sort of blurred over in this analysis. Okay, so this is, I thought it was remarkable. My core facilities are remarkable that there's no specific payment for storage capacity. Yet there's two capital stocks, but we end up with the optimal amount of both, even just payments for electricity itself. Okay, so if you want to know more details about that, you'll have to read the paper. Heavy math in there. And let me use method of monotone comparative statics to look at this model analytically, to look at whether storage and generation are substitutes or complements, under which conditions and which parameters affect investment in each. Okay, and we also do then simulations of the model. So yeah, if you want interested in the model, write me an email. I'll send you a copy of the paper. Okay. let's think about relation to the literature. So only paper we found that has 100% renewables is by Ekorman Virashoki in Energy Journal 2020. But they have other things that are less realistic in their model. Then only Schmalensee, Richard Schmalensee, 2022 Energy Journal models both stochastic demand and supply and investment in both intermittent generation capacity and storage capacity. So those are the major features of our model. On the other hand, his model, basically, there's a day period and a night period, and all the electricity stored during the night is then used up, and we go to the next day of empty storage. So there's not a question of multi-period storage, which we address. So we address multi-period storage. You don't know, should we keep it for tomorrow or the next day after that, or when? So that's not dealt with in the Schmalensee model. We also look at that the longer you store it, it decays, water evaporates in the reservoir or leaks out, electricity leaks out of the battery. We look at pipe constraints. You only can pump a certain amount of water per hour into the reservoir or into the battery and out again. And we also have, rather than a day and night period like Schmalensee, we have hourly shocks. Yeah, so anything can happen in each of them. So there's a paper by Pomeray and Schubert looking at our results rather than a model. So these, sorry, I shouldn't get away from here too much. These here, whoops. These papers are comparing the sort of model setup, looking at the results. Pomeray and Schubert find that generation and storage are complements. Why do they find this? It's because of their model, there's only solar power, which only works during the day. And therefore you have to have storage to supply electricity at nighttime. And so the more storage you have, the more you can utilize solar power, because so the two don't compete with each other during the day. So they operate in different periods and don't compete. And so storage is a complement there to solar power. More storage raises the returns to using solar power, but being able to distribute it at other time of the day. On the other hand, the Holland et al. Paper looked at this issue, and they don't make that sort of non-compete agreement kind of thing. And they find out to substitute storage. You can either more storage, that then reduces the incentives to invest in generation capacity and vice versa. Okay, so that's really the literature. So I'm going to show you this graphical analysis and hopefully get across some of the main points just using that. So it's just this demand curve and a supply curve here, and the price on this axis and the quantity of electricity Q on this axis. And so we have this is assuming a particular generation capacity has been invested in, which we call capital K, generation capacity. And then there is a shock. Each period there's a different amount of capacity utilization of the generation capacity. The amount of electricity supplied to the market from the renewable generation is the stock times the utilization, capacity utilization is period. So K times ZT, okay? And ignoring storage, if we just had solar power or wind power or whatever, we'll just have this vertical supply curve, okay, here. At this level, each hour there'll be a different curve, will be in a different place. So when there's more, the curve will be somewhere over here. When there's less sunshine and wind, the curve will be over here and so forth. It's just a straight up curve, irrespective of the price. That's how much is being generated. It doesn't depend on the price, just a vertical supply curve. And then we'd have a demand curve here, red curve, and the equilibrium price would be B, and the equilibrium quantity would be however much is supplied to the market. There's no choice about that. Okay. Now that would be without storage, would be at point B. Now, when we introduce storage, we get this rising blue, more traditional looking supply curve. Okay. Why is it rising in this section? Well, the basic idea is an opportunity cost, that the scarcer electricity is going to be in next period, okay, the more valuable that electricity is, okay? So when we're to the right of this vertical supply curve, we are discharging electricity, okay? So the further to the right, the less electricity is going to be left stored over the next period. So not knowing what's going to happen to the sun or the wind in the next period, electricity will be more valuable. So it's more costly to release it now rather than receiving the payment in the next period. So that's why the opportunity cost rises the more we're discharging electricity. And when we finally get to this level here, okay, this is the maximum electricity can be supplied to the market, which is the electricity generated in this period, plus the amount stored from the last period, okay? And we have what's called a stock out. We exhaust all the batteries or reservoirs. It's all gone, okay? So that is, then the curve goes vertical at that point, okay? In the other direction, we eventually fill up the battery or the reservoir, and we can't store any more electricity, so we have also potentially a vertical section there. But in between, we have a rising one to represent the rising marginal opportunity cost of releasing electricity from storage in the period. So we have a nice smooth demand curve, and in this example, some electricity is being discharged, and so the equilibrium price is lower than it would be without the storage, and the quantity supplied and consumed is greater than it would be without the storage. Of course, if the demand curve was over here, or the supply curve was somewhere else, it may end up with a higher price than it otherwise would be. And that's when the batteries are charging up. They're adding demand to the market, raising the price of electricity in those periods. Okay. Any questions about this basic setup before I go on to complicate it? Yeah.
I just wonder, the shape of this supply curve with the storage, does it depend on how providers support their expectations about the future? Another all by hour, right?
Yeah, well, yes, but so they're making decision to, yeah, so it's based on what they expect the future price would be given the distribution of shocks and how much is in storage at the moment. Yeah, and how much generation capacity there is. Yeah, so it's a dynamic stochastic optimization in the both the simulation model and theoretical model. Yes, yeah. There's no, yeah. It just assumes it's rational. Yeah. Okay. So we're going to play around a bit with supply and demand curves. Okay. So what's intermittent supply? We have a very simple case here, where there are just two states of the world. One has low supply of electricity, and one has high supply. So sunny, windy day, and a still cloudy day over here. Of course, in reality, it's a continuous distribution model, but for this analysis, we'll just show two potential supply curves. And these are supply curves with storage. So equilibrium when electricity is scarce is up here, okay? And then we'd expect that the batteries are discharging at that point and selling electricity into the market. And when electricity is abundant, the equilibrium is down here, and we'd expect them to be buying electricity at this point. When we compare with intermittent power, these two equilibrium points, and draw a linear combination of the two, assuming, well, it depends how probable the two events are, but C is some intermediate point, and let's assume that that's the mean level. Okay, so what we see here is that at this mean average of the two different equilibria for both low and high supply of electricity, this is the average quantity, the expected quantity. If it was a certain quantity, the point on the demand curve is just down here. But actually, the average price consumers pay under intermittent electricity is higher. Okay, so not at PF, but up here at the expected average price of the two equilibria. So consumers pay a higher mean price under this intermittent generation. Okay, and this is going to sort of help incentivize the storage and everything. Okay, so we can call that a precautionary premium, at least Akshay calls it that. But also at the same time, generators invest more and mean supply is higher because of the higher price, right? So one of the sort of robust results you find from the model is that more intermittency, the more investment in generation capacity, right? So then more consumption of electricity in our future markets, there's more electricity than there is today, because there's more investment in generation capacity as a result of this price premium, okay? As long as you have convex demand curve like this. and there's more investment. So at this price, which is the mean price, the demand at that point on the demand curve is down here, whereas this amount, not demand at the expected price, but the expected quantity in this world of intermittent generation is the amount supplied. So more electricity supplied at a higher average price under intermittency. Okay, so that works out really nicely from just this. As long as you have a convex to the origin demand curve. Okay. And so generation benefits from a higher average price, storage benefits because of price variance under intermittency. So it likes price variance, and generation likes high prices. So both of them are incentivized by this just physical thing of intermittency. What's the effect of storage capacity on the price of electricity? So here in this example, we showed, again, this is the supply of intermittent electricity under bad conditions, and this is the vertical supply curve under good conditions, and then we drew in the one with storage. Okay, so it slopes for a bit across here. So assumption is that the equilibrium without storage at this scarce electricity situation would be the price is lowered relative to the equilibrium otherwise. So batteries moderate those high prices. But at when electricity is abundant, they're buying up electricity, and batteries are raising the low prices. They sort of moderate prices at both extremes. Okay, and without storage losses, the distance of point A from here should be the same as the distance of point B from here. Drew it a little closer, so that would reflect some losses of electricity. So the amount being bought up here is more than the amount eventually supplied when the price is high. So remember here, in this simple example, they're just two states of the world. The reality is a continuous distribution, right? So that sort of losses of electricity from storage are push prices up even more. So storage moderates prices and reduces generation returns. If you draw a line between here, the average price has fallen, okay, between this point A and point B. Okay, and there's going to be, we draw that linear line compared to the previous diagram. We drew one between this A and this B. The mean point is higher than the line between A and B, than between A prime and B prime. Okay, so there's a symmetric effect of generation on storage due to the laws of partial derivatives. Okay, of adding generation capacity with similar symmetric effect. The storage losses, the more, so there's both round trip, pumping water in or electricity in and coming out. There is a loss of power, and there's also a loss due to evaporation. This is due to a drought in this example, but imagine it was a storage reservoir and it's just being evaporated. It's being evaporated off and the level is falling. We're losing electricity from interperiod from evaporation or leakage from battery. Yeah.
Will your calibration just deal with pump storage, or do you also?
It doesn't matter if it's a battery or a storage. Well, I think we set it to some parameters in the battery.
Batteries don't have evaporation losses.
They do. They leak out electricity.
So it doesn't branch differ.
Yeah, it probably does. Yes, I think it's based on the battery. In fact, I don't think it'll make a lot of difference to the results. So these storage losses just throwing electricity away, so they're raising the price intuitively. The more storage you have, the more these losses, and so the more you throw away. Okay. So looking at demand, so instead of intermittent generation, now we assume as just intermittent stochastic demand. So there's more demand in hot weather than in cold weather and so forth, and just one supply curve here. We're just doing one thing at a time. There's an equilibrium down here when demand is low, the equilibrium here when demand is high. Again, the mean price here is higher than it would be under certainty. Okay, there was no stochasticity of demand. And so stochasticity of demand also pushes up average prices and provides an incentive. The question is, what happens when we add more storage? So let's just stop sharing this screen. I don't know. I'm going to draw, let's see if this board is, Yeah, that's a lot better. I'm going to draw a diagram here. I got tired of, well, these other diagrams came out of our paper in this one, not in the paper. So that's another supply and demand diagram like this. We have okay, we have the supply curve of intermittent power. Can you guys see that? You see it up there, of course. Yes, yes. So there's one demand. Well, let's say what I'm going to do. I'm just going to do. Forgot. I'm going to do linear demand to make it really obvious. It's going to do linear demand. Okay. Now, if the demand is okay, so it's a function of price times a shock. Okay, which okay, and so if that's the case, the high demand under linear demand looks like that. Okay. So we had a little bit of storage. This thing is flipping all the time. Okay. Okay. So what's going on here is if we add a little bit of storage, then we have equilibria here and here instead of here and here. So the slope here is flatter than the slope here. So it pushes up the price more when electricity is scarce, when the price falls due to storage when it's abundant. Without losses, these must be the same distance from a demand curve to take electricity in here and discharge it here. So the effect is under demand intermittency, demand variability, is to push the price of electricity up due to the difference in the slope. So it works for this kind of specification. Anyway, okay, now we have losses that's even exacerbated further, right? And so in general, demand intermittency pushes up the price. Okay. We go back to share screen. Okay. All right, so that's the answer to that question. Why is he here? There we go. All right. So add storage and out losses, it pushes the price up with more storage. Oh, and of course, if this was actually a convex curve, as you go in this direction, this curve gets steeper. As you go in this direction, this curve is getting flatter. So that exacerbates the effect even more, pushing prices up when electricity's when demand is low and by much more than it lowers them when demand is high. So losses also raise the price in general. The more storage and more losses in general, this pushes the price up. So what does this mean about substitutability and the competition between the two sorts of generation capital? Well, there's something called Q substitutes or Q complements. Most economists tend to be very sloppy, I find, with their use of the word substitutes and complements. So I wrote a paper back in 2011, which looked at lots of definitions of elasticity of substitution and simple elasticity of complementarity, and pointed out that there are three main meanings of substitutability in economics. The one people most familiar with is when the price of something rises, you look at the one good rises or one input rise, you look at the quantity of the other and how it changes. And according to Hicks' 1970 paper, he called that P substitutes. So the price of one input or good rises, and we look at what happens to the quantity of the other good demanded or used, okay? But he also said there's something called Q substitutes and Q complements, and is when the quantity of one good rises or falls, what happens to the return or price of the other one, okay? It's kind of a reverse question. And goods which are Q complements might not be a P complements, okay? So they don't necessarily two go together, okay? So we look in this paper at Q substitutes versus Q complements. What we're interested in is that there's more generation capacity. What happens to the returns to storage, price of storage, okay? And if there are more storage, what happens to the price returns to electricity? So Q substitutes or Q complementarity. So if adding storage pushes the price of electricity up, they are Q complements. If it lowers it, they're Q substitutes. Okay, reduces the incentive for storage. Sorry, if storage pushes the price of electricity up, it reduces the incentives of generation capacity. So summarizing the graphical analysis, supply intermittency generation substitute would be Q substitutes because they're competing against each other. Under demand volatility, everything pushed in the direction of pushing the price of electricity up. And so they are Q complements. Losses tend to push in the Q complementarity direction and larger storage in the Q complementarity direction. So we don't know theoretically whether they're complements or substitutes, so we need a simulation to find out. Okay, and this is important because you want to know how having more storage incentivizes investment in generations and vice versa. Okay, so what is the size of these effects in a semi-realistic setting? Okay, so we've both calibrated to the Australian market and also to the Texas market. The reason for both of those is they don't have interconnectivity with other markets. So when we look at demand in that market, it's being wholly supplied by generation capacity within that market. And both of them have just pay prices. They just have rewards for supplying electricity, so-called energy-only markets, or primarily for supplying electricity. This results using the stochastic dynamic optimization model, very computationally intensive. We simulate the markets at many possible values of storage capacity K, sorry, it's S, and the generation capacity K, and then to inform an investment decision. And use something called cross entropy method, and we use the supercomputers down the road to do it. Okay, and use a lot of computing time. There's a picture of inside that building, the Gaudi supercomputer. So yeah, we're using that.
What software are you using?
Oh, you have to ask Akshay. Python, I presume, I'm not sure. Yeah, I think. Okay, this is kind of getting on the top of my scale. So
You can go more and then I go more.
No.
I float.
Oh, there we go. All right, yeah, just this one reaches the top of the scale. So this is returns to generation. This returns to storage. You see, we didn't just do one simulation, we did lots, right? For all kinds of storage capacities and generation capacities. Okay, so this returns to generation as we add more and more storage capacity, right? And then each of these curves on here is for different levels of generation capacity. So for high levels of both storage and high levels of generation capacity, K equals 4.9, I don't know why these particular numbers, but anyway, we have this downward sloping curve. So the more storage, the less returns to generators, so they're acting as Q substitutes, okay? When generation capacity is very low though, then they get this flatter part of the curve here. And so adding storage here is actually not reducing the returns to generation capacity when generation capacity is scarce. So when there's a lot of storage relative to generation, they're acting more as complements, Q complements. When there's more generation capacity, you add a little bit of storage, they tend to act as substitutes. And also when there's a lot of both. And then the opposite case here is the returns to storage. As we add, again, same sort of story, these are different levels of generation capacity, allow storage and the returns to storage. So again, substitutes, Q substitutes, they cannibalize each other's returns in these ranges. But over here we see, for low levels of generation capacity, these two curves actually flip over. And this one with a lower level generation capacity has lower returns than the one with a bit more generation capacity. So returns to storage. So here they're acting as Q complements in this small range here. So they can be Q complements, but usually they're substitutes. Usually they compete with each other to supply electricity to the market is the typical effect in our simulations.
I notice your vertical axis is logarithmic.
Yeah. I can't really tell you what those numbers mean, but logarithmic scales, yeah. But this is with very little storage and very little generation capacity, right? And this one calibrated demand curve with shocks, right? So this is obviously very little capacity relative to the demand. So yeah. So they tend to be substitutes.
Very next still trying to understand this Q substitute thing.
Yeah.
Why do you do it? Why do you get this? I'm understanding there's a P substitute in there coming out of standard one.
Yeah.
But why do you want to deviate from this something?
Well, we want to know what are we're looking at what the incentives for investment in terms of return on capital. How does the quantity of the other, how much investment there is in the other capital stock affects the returns on the first capital stock. So that is a class, that is Q complementarity. You add more storage, what happens to the returns to generation? It's incentive to invest in generation and vice versa. Well, then you'd be asking, well, then you ask your question, what happens if we change the returns to generation on the quantity? The price is endogenous in our model. The quantities of investment are exogenous. So what we do is do simulation of lots of different exogenous quantities of investment, and then we choose from for the main simulation, then choose from those, optimize the optimal capital stock based on this distribution. So we can manipulate the capital stock, the amount of investment, and also over the course of a model run, the capital stock is fixed at the beginning, and then the price and storage behavior plays out. So we can't manipulate the price itself. So. And it's a natural question also. There's more investment in generation capacity. What does that do to returns to storage? So it's expressed in that way. But lots of economists they talk about complements or something, and they mean that in fact. And sometimes they mean the P ones, and it's anyway, it's very confusing. Okay. So this is a table of some results with sort of baseline elasticity of demand of -0.1. And this is the baseline simulation with storage and generation. We get this generation capacity, we get this storage. This should be in gigawatt hours, actually, the storage capacity. Yeah, well, storage both has a gigawatt and a gigawatt hour. R1's gigawatt hours, yeah. So, yeah, there should be a little H here, I just noticed. Anyway, yes. This is the amount of generation, the price, and so the price in this baseline simulation is a lot higher than the mean price today. Okay, it's not the median price, it's the mean price. So there are some events when they're very, very high prices, and the amount of stored electricity, that's about 5 hours or so in the simulation. Okay, given the parameters involved compared to the mean level generation. If there's no storage, right, then the generation capacity increases because they're substitutes, right? One sec, let me just finish explaining the table. There's more, because there's more generation capacity, there's more electricity consumed, but of course, like absolutely crazy prices can occur. Okay, yeah.
The generation capacity, I assume, is the plate capacity.
Yeah, they've assumed, my co-authors assumed a 50% capacity for some reason, but yeah, it's a bit high, but yeah. It should be more 25% or something.
I assume capacity factor of 50%.
Yeah. In order to, anyway, I've argued about that, but that's where we're at. Yeah. I don't think it probably makes a big difference to the main results. Yeah. To allow for future improvements in technology. I don't know what the argument is, but anyway. Okay, so this is a distribution of prices. So today's market is quite a very narrow distribution of prices around the mean price. With no storage, okay, you get this bimodal distribution. You also get, it's hard to see here, you get this thicker tail out to extreme prices over here. You see it's blue is above the yellow line for our baseline simulation. You get some moderately high prices here, and you get lots of super low prices here. When there's just too much generation and it's all being basically. So it's bimodal distribution. When you bring in storage, it tightens up the distribution nearer to today's level of prices, but has some moderately high prices here and some moderately low prices here, which the storage makes its money by arbitraging between them. Okay. So you need a bit more variance of prices just to allow storage to do its job. We're going to find in the following ones, storage doesn't need these prices out here. Okay, we can cut those off. It does need these here, moderately low to buy at and moderately high to sell at. Okay, generation capacity more needs these extreme prices. Okay, so looking at the price distribution, the market today, that's the standard deviation under our baseline or under no storage, these blow out totally, but we can look at it also a different way. The skew is also greater under this baseline simulation. As we saw here, there's a sort of more skewed distribution. I mean, actually lower, this blue one is actually less skewed somehow. It's just totally flattened out, okay? And ketosis. If you look at how many times a year price gets above $1,000, it's not that high, really. Okay, it's an extreme price. The Australian market allows a peak price of 15,000 Australian dollars and does tend to hit once a year or so of 10,000 US dollars. So more than $1,000 is not that extreme. So under the market today, it's typically about 3 or 4 times a year in Texas. Under our baseline, it's about 35 times. So it's about every other week rather than every season. Okay, there's a price extreme above 1,000. So that in retrospect is not that crazy as this initial number on the standard deviation makes it look. On the other hand, with no storage, they're happening like several times a day. So storage really does mitigate. It doesn't get down to today's market, in this baseline, but it does mitigate a lot the no storage situation. And then under $1 a day, that happens every couple times a week today. It sort of happens a few times a day in this future market. That's when the storage is buying. And then it happens all the time, every hour, every other hour or something in the no storage situation.
So
Yeah.
there's no storage to counterfactual. We actually have got storage. Right? So just saying what would happen if there was no storage.
Yeah, we sort of assuming a baseline. Well, we don't know what the baseline is, how much storage it's got. But our simulate. This is just statistics from Texas market today.
Right, what I'm saying is Texas has got some storage, hasn't it?
Well, it has fossil fuels
Right.
and hydropower, which we don't have in our model.
It's hypothetical.
So this is what the market looks like today. If you want to compare our future markets to a market today, this is the comparison.
I just wanted to do about the storage.
Yeah. So no, it's got fossil fuels and coal and gas and hydropower and stuff as well today.
A little bit of storage as well.
Yeah, probably some storage, yes, and some intermittence. Yeah. So this is a typical market today. These are models with pure intermittent power and storage, or just intermittent power and no storage down here, which only works at all because our it'd be crazy. Anyway. Yeah.
So I wonder if so today's numbers are just empirical data you observe in the real market.
Yeah.
So to make baseline.
And we set our demand curve calibrated on that. Yeah.
Okay, so I wonder if is it possible to calibrate the baseline to today's number? Because when I did this generator models, we usually just calibrate the baseline.
Well, yeah, but
the real data as much as possible, and then look at it.
we do. Well, by calibrate, we assume we calibrate our demand function on the real data, right? And then we use various parameters from the literature on the costs of generation and storage capital and the round trip losses and all these things, and build our model. So it's the demand curve is coming out, and then some idea about the variance for intermittent generation from a literature. And so a world with just intermittent power is so very, very far from so our model, okay, so I understand the difficulty. So we don't have a fossil fuel thing in our, which can provide baseload power in our model. So we'd have to build a model that had a baseload power in order to simulate today's market, and we don't want to do that.
I think the question is, are you sure that this should be called baseline? Shouldn't it be called something else?
Oh, that's great. It's our sort of using the parameters from the literature and the calibrated demand function. We then explore crazy other scenarios.
Just might be a bit misleading in terms of terminology because it's similar to baseload.
Okay.
Well,
So problems
what it is today.
Yeah. It's the market of the future under our sort of standard set of parameters.
100% renewable.
100% renewables
With
in
storage.
with storage.
Maybe a better name than baseline.
Yeah.
That's
Okay.
the point.
It's a long thing to write every time. We might. So, yeah. Okay. Good point. Yeah. Future. Yes. Okay. The real. Yeah. Okay. So we got 35 events a year. The price is goes over $1,000, and the mean price. Okay, going back to here, the mean price is much higher than in today's market, which we said this is going to happen because my supply and demand analysis I showed you, we have more yeah. So, but can we try and mitigate that high price and the high variance without destroying investment? Okay, so we look at two different strategies for that. So this is like the policy analysis now. So price caps. So markets today, even the Australian market's the craziest of all. It has a price cap at 15,000 something Australian dollars a megawatt hour. So we start here at $10,000 US. The Texas one today, I think it's about 5,000. I'm not sure, somewhere in that range. So we have a $10,000 cap, a $1,000 cap, a $500 cap. Okay. And under the $500 cap, we get the mean price down to near today's levels. Okay, under the so that's the price. That's with no cap. That's with $500, with $1,000, with $10,000. So caps definitely bring down the mean price. The returns to storage, well, no price cap is this, and these are the results with these different price caps. So they're almost the same number. So the price cap has no effect on incentives to invest in storage, pretty much. Storage is arbitrage between moderately low and moderately high prices. It doesn't really need these extreme prices. On the other hand, generation capacity, the returns to generation capacity are reduced by the price caps. Okay. So if anything, we need to sort of incentivize generation capacity rather than storage capacity. Storage capacity won't be worried by these volatility reducing price caps. Okay. Then we look at also as another option is more demand flexibility. So the consumer elasticity demand is something like probably near a 0.3 for electricity based on the literature. Whereas in the wholesale market, it's a lot of models, like Schmalen's model assumes it's zero. It's not. That seems too extreme because large users are willing to reduce their consumption when the price is very high. So I doubt it's actually zero. But we look at the 0.1. 0.1 is our baseline. 0.3 is more demand flexibility. So in more demand flexibility, you get lower generation capacity, lower storage capacity, less electricity consumed, in fact, because this is lower. Okay. The mean price also falls under the the greater elasticity of demand and the amount stored. So more demand flexibility can also reduce the mean price, but it also it's an alternative strategy to multiply prices. Yeah.
In your tables, generation is supposed to be gigawatts rather than gigawatt hours.
Generation capacity is gigawatt hour. Storage capacity should be gigawatt hours.
What about generation?
Should be gigawatts. Generation capacity and generation could be either gigawatts or gigawatt hours. It doesn't matter. We assume an hourly step. So normally we talk about generation as gigawatts anyway. Usually, sort of in an instantaneous power, but are an hour step, so it could be gigawatts or gigawatt hours, doesn't matter. Storage capacity should be gigawatt hours because there is we're looking at the amount stored and it could go over multiple periods. Yeah, so there is the hour thing missed off the storage capacity once. Thought I'd fix that, but anyway. Yeah, so this is with the price cap and the demand flexibility. And of course, again, there isn't much effect on the returns to storage. Prices are moderated, actually moderated less than under a more inelastic demand by the price cap, the mean price. The returns to storage generation are better under demand flexibility, increased demand flexibility. So what we're thinking of here are even making retail customers more facing the wholesale market price, basically, or strategies to sort of switch people on and off or something. So we're not specifying exactly what, but nearer to the actual consumer elasticity of demand rather than the current less elastic wholesale market elasticity of demand. So the two combined here gets up to, with a cap at 10,000, gets up to almost the uncapped generation returns. So you could do both, sort of a not so extreme price cap plus demand flexibility, you get almost the optimal amount of storage and generation capacity. Okay. So we think, based on this very simplified world, right, that sort of energy only market is feasible. The market certainly has an equilibrium and so forth with 100% intermittent power and storage. Storage makes the market a lot more like today's, but not exactly, but with the price cap in place and more demand flexibility. But sorry, even with price caps in place, there's sort of optimal amount of storage is incentivized in our model. Okay. The combination of more demand flexibility and price caps is a sort of an alternative sort of capacity markets and so forth, right? To try to get a world that's not too volatile and has sufficient investment. Mostly we find the generation and storage as a substitute, sort of against sort of naive sort of common wisdom, but it must be good for each other. They compete against each other mostly. Okay, so those are sort of our main conclusions from our research. And well, what's wrong with our model? Lots of things, right? Very simplistic treatment of demand and supply shocks. I think is the most important thing, probably. So they're both predictable. In reality, both predictable and stochastic components. So a theory sort of suggests that results hold up with deterministic components as well. So we know it's going to be nighttime, right? In this model, we assume we don't know it's going to be nighttime necessarily. Okay, so we just want to make it simpler. There's also correlation. If it's sunny today, it's probably going to be sunny tomorrow, at least in Canberra. Okay, we assume it's just random in our model, right? And there's also cross correlation between demand and supply. Not perfect, which results in the problem of maximum generation during midday, maximum demand in the evening. But when it's hot and sunny, we get a lot of solar power plus a lot of demand. So we assume that there's a zero cross correlation, right? So there are, I repeated the first point again for some reason, but yeah. So yeah, so I would probably as a next step look at making the shocks more realistic, and then looking at sort of a retail generation divide, so we can play around with policy choices there better. Main changes are. Okay, so welcome to take general questions.
Professor, this is